Section 4.2, Modeling with Linear Functions. Here we're going to look at a 4-point strategy on how to solve problems with linear models. The first thing we want to do is we want to read the problem very carefully. We want to make sure we try to identify any important information, such as anything that identifies values that we can use to plug in for variables. If the model is supposed to be linear, can we identify the slope of our linear equation? We do want to try to keep information organized, so it does help to draw pictures, especially in geometry problems, or define coordinate systems, such as setting a specific location or a time to be 0. And last, identify the question asked. You want to know what your end goal is before you try to make any plans and work things out. After you've carefully read the problem and processed the information provided, write a formula for the function. For this section, these formulas will be linear, but this strategy can be applied to other problems with other types of functions. Then, once we have your formula written down, you want to plug in any known quantities into your function. Then, you want to solve or evaluate the function. After you solve or evaluate the function, make sure you double check the question and make sure you answer it fully. Just because you solve an equation or evaluate a function doesn't necessarily mean you have the answer just yet. Always go back, reread the problem, make sure you are answering the question fully. Also, remember to put the appropriate units so that way there's full context on what the number represents. In this example, 100 squirrels lived in my backyard in 2023. By 2024, the squirrel population in my backyard grew to 120. First, we're going to find a linear equation for the squirrel population P in my backyard T years after 2020. So first, we have to be very careful when we interpret our variables. We're not just using T for what year we're in. We're using T to represent the number of years after 2020. So the year 2020 would be represented by T equals 0. If we take a look at the years we have information for, first the year 2023, which is 3 years after 2020, which means T would be set equal to 3 to represent 2023. And we're told the population of the squirrels in 2023 is 100, so P of 3 would equal 100. Now the next year we have information for is 2024. Since 2024 is 4 years after 2020, that means we've set T equal to 4. Since there are 120 squirrels in the backyard during 2024, that means P of 4 is equal to 120. Now, each of these function values we can translate to order pairs. P of 3 equals 100 means we have the point 3, 100 on our graph, while P of 4 equals 120 means we have the point 4, 120 on our graph. So by translating the information, we're trying to find a linear equation that passes through the point 3, 100 and 4, 120. Well, if we think back to problems we were doing last section, when we're given 2 points that we know a linear equation must pass through, I would first find the slope and then use my point slope form. So for my slope, I'll have 120 minus 100 all over 4 minus 3. And we get that our slope is 20. Now from there, we can write our point slope form. I'm going to use the point 3, 100 for my point slope form. But instead of writing it as y1 minus y equals m times x minus x1, because our dependent variables are p, our independent variables are t, the point slope form I'm going to use is p minus p1 equals m times t minus t1, where I replace the y with p and the x with t. So when we plug in our information, we get p minus 100 equals 20 times t minus 3. Now we'll manipulate our point slope form to obtain the slope intercept form. And from there, we get that p equals 20t plus 4. And if we want, we can use function notation. So instead of just writing p equals, since our population does depend on time, we can put p of t equals 20t plus 4. Now that we have the equation, we can answer the second part. We want to predict the number of squirrels living in the backyard in 2026. Now, this is where, again, we have to be careful with what t represents. T represents the number of years after 2020. So if I'm talking about the year 2026, I'm not replacing t with 2026. The year 2026 would be represented by t equals 6, since 2026 occurs 6 years after 2020. If I want to figure out what the squirrel population is in my backyard in the year 2026, I want to plug 6 into my population function, meaning I'm trying to evaluate p of 6. And I get that there would be 160 squirrels. In many problems, we're using variables to represent unknown quantities that represent something in the real world. Because those variables represent something in the real world, there are natural restrictions that come with them. This is when we start talking about the practical domain. In many applications, we restrict the domain based on what is actually possible in the real world. And this restricted domain we call the practical domain. An example of a practical domain comes into problems involving throwing balls or launching rockets. Suppose that h of t represents the height of the ball t minutes after being thrown. Since t represents the amount of time after the ball is thrown, it wouldn't make sense for t to be negative, because when t is negative, nothing's happened yet. The ball hasn't been thrown. So our first restriction is that t has to be 0 or larger. But then once when the ball lands, it's no longer falling, it's no longer moving. So it wouldn't make sense to make t larger than the amount of time it takes for the ball to hit the ground. So that'll give us a restriction on t. T would have to be between 0 the time we throw it to the time when the ball hits the ground. Once when the practical domain is determined, the range that corresponds to the practical domain is called the practical range. Taxicabs are a popular way to get from place to place in New York City. A taxi ride costs $5 plus an additional $1.50 per mile. You only have $101. First, we're going to write a function for the given scenario. We're going to let m be the distance that we travel in the cab measured in miles, and we're going to let c be the cost. In this scenario, the cost does depend on how far the taxi cab takes us. So using function notation, we're going to have c of m, and this is going to equal some expression involving m. But now let's think about how would we calculate the cost of our taxi ride. Well, it tells us that it costs $5 plus $1.50 per mile. So we know no matter what, just for getting into the cab, we have to pay $5. Plus, well, $1.50 per mile, and we're traveling n miles, then we have to add 1.5 m. So the $1.50 would be the value of our slope, while 5 is our y-intercept. But there's our function. C of m equals 5 plus 1.5 m. Next, we want to know what is the maximum number of miles you can travel. Keep in mind, we only have $101 in our pocket. So our cost must be less than or equal to $101. If it goes more, then we get in trouble with the taxi cab. So from this, we have the inequality that our cost, which is 5 plus 1.5 m, is less than or equal to 101. Now we can solve this inequality, and we get that m must be less than or equal to 64. So what is the maximum number of miles we can travel? The maximum we can travel is 64 miles. Now, what is the domain of the function? Our domain would represent all the possible distances we can travel in the cab. Now, when we're finding the domain here, we are determining what is actually physically possible. Well, we know the farthest I can travel is 64 miles thanks to the previous part of the problem. So it wouldn't make sense for me to travel more than 64 miles. I don't have enough money. Does it make sense for me to travel a negative distance? No. So I can travel anywhere from 0 to 64 miles. Now, what do I put around the 0 and 64? Brackets or parentheses. Around the 64, we get a bracket. I know I can travel 64 miles. I have enough money to cover the fare. Well, what about 0? Should we put a bracket or a parenthesis? Would it necessarily make sense for us to travel 0 miles in a cab? Not really. But is it possible for us to hail a cab, pay for it, realize, oh, wait, I don't want to go anywhere, and get out and just lose the money? Yes, you could. So even though it seems illogical, you could physically travel nowhere because you decide not to. So our domain would be the closed interval 0 to 64. Keep in mind with practical domains and practical ranges, it's about what's physically possible, not what would necessarily just make sense. Next, what is the range of the function? Keep in mind that 1.5 is a positive slope. This tells us our function is increasing, and we know because our model is linear, we're making a straight line. So if we think about our range, what is the highest possible cost for this taxi cab? Well, the highest possible cost is $101 because that's all the money we have. But what is the lowest cost? Well, because our line is increasing, because we have a positive slope, our lowest cost is going to occur when we travel the smallest distance. Well, here, the smallest distance we can travel is 0, and C of 0 would equal 5. So we'll put 5 there as part of our range. And we're going to put square braces around the 5 and the 101 because we can have a taxi cab that costs $5 where we travel no miles, or we can have our fare be $101 where we travel as far as possible, which is the 64 miles. Next, let's talk about revenue, cost, and profit. We're going to let X be the number of items of a particular object that is for sale. The revenue, which we denote as R of X, is the amount of money that you obtain from selling the X items. The cost, C of X, is the amount of money that you spend to make X items. The profit, which we're going to denote P of X, is the difference between revenue and the cost of the X items. So from the definition, P of X would equal R of X minus C of X. A lot of times when we discuss profit, we always associate that with something positive, that we had a net gain in money. However, here in this context with the functions, our profit could be positive, negative, or 0. If P of X is negative, that indicates that you lost money. This occurs because the cost was greater than the revenue you brought in. If our P of X is positive, that means you made money and your revenue was greater than your costs. And lastly, if P of X is 0, this means cost and revenue were the same. We refer to this as breaking even. So whenever you hear the phrase break even, you can either interpret that as the profit is 0 or the cost and revenue are equal. Suppose I own a company that makes and sells thingamajigs. It costs $500 plus $5 for every thingamajig made. I sell each thingamajig for $10. First, we're going to write a function that represents the company's revenue when X thingamajigs are sold. And we're going to call this function R of X. When writing our revenue function, one thing to keep in mind, the way we can calculate the revenue is we can take the number of items that we sell and multiply that by the price for an individual item. In this problem, we're letting X be the number of thingamajigs that are sold. So the number of items sold is X. But what is the price for each thingamajig? In the problem, they tell us a thingamajig costs $10. So the price for one thingamajig is $10. So we'll multiply the $10 with the X thingamajigs, and our revenue would be 10X. Next, we want to write a function that represents the cost to make X thingamajigs. We're going to call this C of X. Now, going through the problem, we have to identify what all of our costs are. First, we're told that it costs $500 plus $5 for every thingamajig made. So no matter what, I have to spend $500. This $500 is often referred to as a fixed cost. This is a cost that we have to pay no matter what, pretty much the price of operation. Now, the $5 for each thingamajig, well, if I'm producing X thingamajigs, it's going to cost me an additional $5X, which I have to add to the $500. The 5 we would refer to as the variable cost. This would represent how much money I would have to spend for each thingamajig made or each item made. We get our cost function, C of X equals 500 plus 5X. Next, we want to find our profit function. Our profit function, P of X, equals the revenue function minus the cost function. We found the revenue function in part 1. We have the revenue function as 10X. We found the cost function in part 2. That's 500 plus 5X. Notice that I'm putting the 100X and the 500 plus 5X in parentheses. This is so that way I remember I'm taking the first function and subtracting the second function, and I avoid any sign errors. Now, in the first set of parentheses around the 10x, I don't need them, so I'll drop them. But it's better to have them and not need them and then drop them later than to not have them, never put them there, and it turns out you do need them. To get rid of the second set of parentheses, I do have to distribute into -1. And then to finish up, I can collect my like terms and get P of x equals 5x minus 500, which would represent my profit for selling X thingamajigs. In the fourth part, they want to know how many thingamajigs must I sell in order to break even. There's two ways we can approach this problem. The first approach is we can use the fact that breaking even means the profit is 0. So I can set P of x equal to 0 and then solve the resulting equation. So replace the P of x with what we found in part 3, and I have the equation 5x minus 500 equals 0, and I get x equals 100, which tells me I would have to sell 100 thingamajigs to break even. As for approach 2, the other way we can interpret breaking even is when our revenue equals our cost. So with this interpretation, we would have that 10x, our revenue function, equals 500 plus 5x, which is our cost function. And we'll still solve the equation. And after we solve the equation, we still get x equals 100. Doesn't matter which method you prefer, either setting the P of x equal to 0 and solving, or setting R of x equal to C of x and solving. Both approaches represent the same thing and will give you the same answer.